Alright, time for another DrivePhysics.com, debatephysics.com also, but the debaters won't stay on the subject, won't cite anything called real evidence, won't do anything to rationally participate in a filtering of the truth through testing. They just really don't want their theories tested, and that's the simple truth. And such. So, Wikipedia will tell us what we must believe, and very quickly they start talking about spin and other kinds of, nonsense as regards to electromagnetism as a subject. And of course, that's all just bullshit, frankly. And so I will explain it more simply and more, I think, accurate to the truth. So we know what a magnet is, right? That's just not even a little bit complicated. It could be called a dipole. We know that one side, let's make the north blue and the red south. Okay, that it does something here that's exactly the opposite of what it does here. So if I hit it with the same force, the two things, this one will do this, okay, and this one will do this, okay. So it's an inverse reaction. That's what dipoles do, is create inverse reactions. And what we also, I think, know is that you can put a bunch of these little magnets together, right? You could just put a whole bunch of them, so just imagine millions and billions of them. And they will compatibly stay in these conditions, okay, and they can be next to each other in just the inverse arrangement, and it just works, okay. Red, blue, red, blue, red, blue connects. It all fits together, and you can make an object that is consolidating all of those little magnets into what will turn into one big magnet, which I drew wrong. This would be the blue end, obviously, and this would be the red end. All right. So big magnets are made out of little magnets. And so this really is just about the fact that the charge comes in two elements, okay, plus and minus, however you want to describe that. And the fact is you can just simply make a dipole, okay? And if you align all these little dipoles, okay, if you align them all in the same orientation, they will amplify each other's effect. So the change they create in the environment, okay, will be amplified. Simply stated, that's what's going to happen. Okay, blue goes in, blue gets converted into red, and then red comes out. The dipole acts as an inverse converter of the energy, and you could understand that that's all you really need is that these two things change the environment in the opposite way. So the same thing goes in, a different thing comes out. So if red comes into both of these, in one case this is going to move, it's going to be pushed, which is the same as the red coming out. And in this case, there's going to be a blue force coming out, and vice versa. And you can understand the whole system can work that way. But it's really just about monopoles and dipoles. That's it. And dipoles will react to a magnetic field. Monopoles can't see the magnetic field. All they see is force hitting them, and that's it. They can't turn or in some way move in some weird way because of that. They're either pushed by a force or they're not. I suppose, yeah, and they're always smaller than the dipole. So you have to understand the monopoles are intrinsically smaller than the dipoles. I don't know if there's much. Oh yeah, well, we're talking about electro, so let's do the electro part. All right, so that's a natural magnet. Let's call it our static magnet. So you can make a piece of iron into a magnet by tapping it or doing something else. You have a piece of iron, you put it in a field that has a polarity to it. That is, it has a red and a blue side, so to speak. And all of the stuff inside of here, if I tap it, all of it will start to line up and, participate in being attracted to this and repelled by that, each unit, and so it will balance to the field that it's in, and so all of the little bits inside of the iron will start to line up, and they'll all line up in the same way, and you'll end up with a magnet. And the same thing happens to the conductor. So when you do this to a conductor, piece of metal, All right, it doesn't have to be magnetic, a piece of copper. It doesn't have to be a natural magnet, that is a static magnet. It can just be a piece of conductor. And the fact is when you send the electricity through it, it's going to duplicate this effect in the sense it's going to take atoms that are, say, in this configuration, just roundish, balanced, and it's going to change their shape. And by changing the shape, it's going to change their capacity to produce a field in the sense that they're now going to look different. So they're going to look redder from the side and bluer from the bottom and the top. It's going to polarize the atom. Now that obviously produces a perpendicular effect. That is, you push a force in this way and you create an effect that way. The fact is the force probably goes this way, but regardless, because the momentum of the electron is in and out, but the momentum of the force you're applying is this way. So you end up with something that's a combination of those two momentums. So the simple truth is that, okay, you put a current in and you end up creating an appearance of the atoms where before the red wasn't visible, you're making it visible. And so now from this angle of view, the red can be seen because you squished the atoms. And so that's what happens. When you put the electricity in, you change the shape of the atoms essentially. I mean, it's an analogy. It's probably not perfect. But you're basically compressing electron pressure in one direction and expanding electron pressure in the other direction. So you can understand electrons are getting pushed further apart this way, and they're being pushed closer together this way. And that has to balance out. And if you keep pumping current through, it's going to maintain that weird shape. It's going to keep oscillating from this to this, from this to this, from this to this. And that oscillation is the magnetic field that you can induce into another wire. All right, so it's something that simple. It's not very complicated. So the energy of the magnet is just how the magnet reflects the universe. The universe comes in a certain way, a mixture, okay? And the simple truth is the mixture is in some sense segregated, okay, in the sense that more of it will come out one side that comes out the other side, and that's the nature of the magnetism. So no force irradiates out of a magnet. It's just that it looks different. So the piece of steel looks, let's just say this is purple. Okay, so it looks purple, and when it's magnetized, okay, it changes its appearance, so now it looks more blue at one end and more red at the other end from certain points of view. All right, I don't think you need much else than that to start with anyway. But it can be simply understood that this is just about tiny atomic dipoles. And the fact is that by changing the pressure on an atom, you change the appearance of the atom, and the appearance can be seen. This looks different than this, and this. And this. Those are different patterns. And the other stuff looking at it can see. Some of the dipoles can see the pattern. They can be either compatible to it, that is, they can be this way or that way, and they can react to the pattern. And so you change an atom over here in terms of its appearance, and you end up doing the same thing to this one because it can see the field this one's reflecting. It's like I could shapeshift into a rhinoceros or something. You would react, rhinoceros. And then I go back to being not a rhinoceros, right? You're going to end up reacting because you can see the pattern. So it's just about what other objects see in terms of physically are affected by. They don't see with eyes, they see with their entire object, whatever, substance, with their substance. All right. So we will move on to the actual crappy page telling us what we must believe because they've proven everything. No, not really. All right, so let's begin with the statement that the biggest thing that makes magnets is dipoles pointing in the same direction, oriented in the same direction. The more dipoles you have oriented in the same direction, the more magnetism will be created. And again, it's not created, it's just an effect. It's just how it's going to reflect force hitting it. Dipoles reflect the force different than single elements of charge. All right, in physics, electromagnetism is the interaction that occurs between particles with electric charge via electromagnetic fields. So again, that didn't say anything about the key point, which is dipoles. Dipoles create magnetism. The electromagnetic force is one of the 4 fundamental forces in nature. Okay. So again, it's this idea that you're going to call it electromagnetic when really it's a dipole force for magnetism, and it's charge for the monopoles. So we know that it's all based on charge. If you didn't have the opposite charges of electrons and protons, you can't make a magnet, you can't make electricity. All right, it is the dominant force in the interactions of atoms, so the exchange of electrons. Electrons banging into electrons is the fundamental action in the universe. You can't get to the protons, they're inside the nucleus. They don't have much to do with anything. So it's all about electron pressure. So that should be a key point made. All the interactions between atoms, 99% of all the interactions are interactions between electrons. And molecules. Electromagnetism can be thought of as a combination of electrostatics and magnetism. So I mean, it's just, we just put these 2 words together and that's it. Okay, what it really is a dipole phenomenon. It really should be understood as that, which are distinct and closely intertwined phenomena. They're only intertwined in the sense that you have to make a dipole. You have to put one kind of charge next to another, the opposite kind of charge, and make something that has polarity. All right. Electromagnetic forces occur between any 2 charged particles. So it's wrong to call it electromagnetic because it's just charge between individual charged particles. They're obviously not magnetic if there's no dipole. So an electron and a proton are not electromagnetically going to do something. They're going to do something based on the structure of charge, the fact that they are distinctly different objects, but they are not a dipole yet. They cannot make magnetism yet. All right, electric forces cause an attraction between particles with opposite charges. So this is just a lie, okay? I mean, it's just nonsense. The electric forces don't do anything to create charge. Charge creates the electricity. They just have it completely backwards, as always. All right, and repulsion between particles with the same charge. So again, it's not anything to do with any electric anything. It just has to do with the fact that the charged particles have a distinctly opposite effect to the same force. That's the simple point to make. While magnetism is an interaction that occurs between charged particles in relative motion. So again, it has nothing to do with motion. You don't need to move anything to create magnetism. Just a complete nonsense. It is a static, real condition. I put these little charges next to each other and I stack them. None of them have to do any movement for the magnetism to be created as a phenomenon of the external world. The magnet will produce the magnetism. There needs to be nothing moving. It's just a nonsense. These 2 forces are described in terms of electromagnetic field. So again, the field is just one field. It is not electric field and then some other thing called a magnetic field. It's all one field of energy, and all you're doing is changing the pattern of the field. All right. Microscopic changes occur. Microscopic changed objects, charged objects, are described in terms of Coulomb's law for electricity, and it's about charge. It's not about electricity. It's about charge. And Ampere's law force for magnetism. Well, obviously that's about electricity. So again, it's too much of a nonsense. And the Lorentz force describes microscopic charged particles. The only thing there is charge, and that is described in Coulomb's law, but it's just charge. All right, electromagnetic force is responsible for many chemical and physical phenomena observed in daily life. So far, we're right through this first whole pig pile of crap, and they haven't mentioned the word dipole yet. They haven't said a thing about a dipole, and it's essential to magnetism. There's no such thing as magnetism without dipolarity. All right, the electrostatic attraction between atomic nuclei and their electrons holds atoms together. So again, that's charge that holds them together, not magnetism. Okay, electric forces. So again, they just keep saying this crap. That's just crap. There's no electric force. There's no magnetic force. There's just the force. Are also allow different atoms to combine into molecules, including micromolecules, whatever that is. It's such a silly term, such as proteins that form the basis of life. So they always have to throw in some little nonsense about gooey chemistry, as if that has something to do with this hard physics. Meanwhile, magnetic interactions between the spin and angular momentum. So there's no such thing as spin and angular momentum. It's not a real thing in the micro universe. It's not a concept, really. It really doesn't happen. The only thing spinning, perhaps, are the dipoles of neutrons. Neutrons are the elemental dipole. It's likely that when they exit an atom, they have a rotation, and that rotation ends up breaking them apart. But spin doesn't do anything inside of atoms. Magnetic moments of electrons, so there's no such thing. The electrons are one thing. They do one thing only. They don't have a magnetic moment. They just have a position relative to a proton. That's all they ever have. They can't personally do anything. They're just a little blob that's charged. A red force comes in, it pops out blue. A blue force hits, it moves. That's it. It's just transferring momentum. In one case, it collects the momentum. In another case, it doesn't collect the momentum. It's just that simple. It doesn't do anything else. It can't have a spin. It can't have any kind of orientation. Okay, it's just one thing and one thing only. Also play a role in chemical reactivity. Such relationships are studied in spin chemistry. So just all absolute nonsense physics. They just make all this crap up, talk about like it's a real thing, like they have real evidence for any of this crap. They have no evidence for any of it. Electromagnetism also plays several critical roles in modern technology. So now they're going to say, their physics invented the wheel, when no, it didn't. Electrical energy production, transformers and distribution, light, heat, and sound production and detection, fiber optics and wireless communication. Now, obviously, fiber optics doesn't have anything to do with magnetism. So again, just bullshit. Sensors, computational electrolysis, electroplating, mechanical motors, and actuators, solenoids. So obviously the capacity to make magnetism out of electricity hugely, gives you lots of options. So it's a great innovation. So nothing, I'm not saying anything against that. But again, to put fiber optics in that category is just absolute bullshit. Okay, there's no electromagnetic element to a frickin' photons going through a glass tube. All right. Electromagnetism has been studied since ancient times, so that's even a little bit dicey a term. Many ancient civilizations, including the Greeks and the Mayans, created wide-ranging theories to explain light, static, electricity, and the attraction between magnetized pieces of iron ore. Yeah, well, having elaborate theories doesn't mean much, especially when the theories are the Gremlins did it. However, it was not until the late 18th century that scientists began to develop a mathematical basis. So again, this crap about how somehow formalizing it into some simplification called math somehow enlightens you. When, no, that's likely to deceive you. Okay. And again, the math, like in the two-slit experiment, the math is so simple. Okay, the basic functional math of dipoles is so simple, and they're making it sound like somehow it has to be complicated. All right, basis for understanding the nature of electromagnetic interactions. In the 18th and 19th centuries, prominent scientists and mathematicians such as Coulomb, Gauss, and Faraday developed namesake laws which helped to explain the formation and interaction of electromagnetic fields. They just wrote down the tendencies. Okay, and that's it. I mean, that you can make more magnetism by using low voltage and high amperage. Okay, shove a lot of electrons in, make all the atoms have to do work, and you can make more magnetism that way. That's not, is that written down? We got to write that and call that somebody's law? That's not somebody's law. All right, that's just the fact that this is how it functions. All right, the process culminated, so they think they culminated something in the 1860s with the discovery of Maxwell's equations. So again, they think they discovered something. All he did was take their equations and put them in the same, put them in a little pile and say, here's a set of equations. All right, a set of 4 differential equations which provide complete description of classical electromagnetic fields. So again, it's not complete at all. It's just a nonsense to say it is. They had to be revised over the years, so just more bullshit. Maxwell's equations provided a sound mathematical basis for the relationship between electricity and magnetism, and scientists has been exploring for centuries. So again, it's just understanding there's a certain amount of effect you're going to have, and you can figure that out, just like we can figure out there's a certain resistance to a wire, and you can figure out how long the wire is and how thick the wire is, and you can figure out how much electricity you can shove through it. Not exactly brain surgery, so to speak. And predicted the existence of self-sustaining electromagnetic waves. So again, nonsense. Self-sustaining electromagnetic waves. No, a clump of energy. Okay, so again, they won't even let you believe what Newton believed, okay, which was, yes, it's a clump. And the clump moves through space with a velocity, and when it hits something, it has momentum. Not very complicated, but you're not allowed to believe the not complicated theory. So Maxwell postulated, okay, so this is the crap Maxwell made up, okay, so I could say Faraday postulated that there's a bunch of gears inside of a material, okay, and there's little idler wheels, and there's all kinds of, axles and all kinds of bullshit. Do I have to believe that because Faraday believed it? I don't think I have to. All right, Maxwell postulated that such waves make up visible light, which was later shown to be true. So again, this is just more bullshit that it has to be a wave, okay? The fact is they figured out that the light has a frequency, okay? And you figure out that, well, here's the frequency range that we see. But yeah, there's a whole bunch of numbers going that way, and there's a whole bunch more numbers going that way. So, wow, let's do this brilliant speculation of saying, gee, you know what? There might be stuff we can't see that way, and there might be stuff that way we can't see, but it's still there. I mean, again, are we going to call that a brilliant insight? That, oh, if somebody hadn't figured out how to say those words, of course, it's obvious. Once you knew it was a frequency, you know that, well, if it's 40 hertz, and what's 30 hertz look like? What's 20 hertz look like? I mean, it's an obvious thing to say. It's going to be almost the first thing that'll come to mind if somebody says, here it is, it's 40 hertz. You're going to say, well, what's 39 hertz look like? And what's 41 hertz look like? Come on. Gamma rays, X-rays, ultraviolet, visible, infrared, radiation, microwaves, and radio waves were all determined to be electromagnetic radiation, differing only in the range of frequencies. Yes, exactly. The same exact stuff, clumps, just coming at a different rate. Okay, so it's all the same bullets, and all you're doing is firing them at different frequencies, and different frequencies will have a different effect on the matter depending on how easy it is to tip, so to speak. It's all just about throwing things and tipping points. In the modern era, scientists have continued to refine the theorem of electromagnetism to take into account the effects of modern physics. So now we're just going to talk about relativity and nonsense. So again, all this whole section, did they mention the word dipole? And you know, and I know, okay, it's essential to magnetism. You can't have anything called electromagnetism without talking about fucking dipoles. So what's the point? All right, in the modern era, scientists have continued to refine the theorem of electromagnetism, taking into account the effects of modern physics, including quantum mechanics and relativity, the theoretical implications of electromagnetism, particularly the establishment of the speed of light. So again, the establishment of the speed of force. So again, these huge mistakes of physics. I mean, obviously it's the speed of force. All the forces move at the speed of light. So why are we calling it the speed of light? Why don't we call it the speed of magnetism? Why don't we call it the speed of gravity? It's stupid. It's the speed of force in the universe. All of these things are forces. It's just bits of energy traveling, and we can't see it because it's really goddamn tiny. All right, based on properties of the medium of propagation. So again, the medium. What is the medium? So they're against an ether. They don't believe in an ether, but there is an ether. It's just such bullshit. All right. Permeability and permutivity. I mean, this made-up concepts, made-up constants. Okay, these things were never measured. There was never a measurement of the permutivity of space or the permeability of space. These are just made-up mush. Helped inspire Einstein's theory of special relativity, which again is just a non-answer to a question. What's causing? Oh, well, there's no real cause. I mean, it's just this magical force, and it just magically endows you with these capacities to bend time and warp space. All right, anyway. Meanwhile, the field of quantum electrodynamics has modified Maxwell's equations to be consistent with the quantized nature of matter. So, again, how is it consistent at all? Quantum waves. No, those aren't consistent theories. There's no consistency at all. Discrete bit and, quantum of energy and wave, spread, nonsense. No, it's just they can't be compared. All right, in QED, the charges in the electromagnetic field is expressed in terms of discrete excitations. What is that? What's a discrete excitation? No, the real truth is electrons do this. Okay, they move towards, they compress a force, increase the frequency. They move away, they expand the force and decrease the frequency. All right, particles known as photons and quanta of light. So nothing. They said nothing about dipoles. Nothing about what a magnetism has to be. So if you're going to call something electromagnetic, you're going to have to talk about dipoles. All right. Ancient world, I don't think we'll bother with that, right? Yeah, no, let's not bother with the ancient world's understanding of a magnet. All right, 19th century. Electricity and magnetism were originally considered to be separate forces. And you're still talking as if they are. So again, where have you grown up and changed that point of view? It's all charge. It's just the interaction between electrons and protons. There's nothing else to the elemental universe. Again, that's one of the key things you have to understand somewhere in all this physics. And they won't say the words because they don't believe in the simple universe. But the universe just is made up of force and two kinds of matter. Positive, electron, proton. That's it. Put two of them together, that's a neutron. That's it. You're done with particles, okay? There's no neutrinos. There's no muons. There's no taus. There's no other particles doing anything. There's no other structure. There's just electrons and protons. That's it. All right, this view changed with the publication of James. So again, Maxwell. In which the interactions of positive and negative charges were shown to be motivated by one force. So they can't be motivated by one force. So that's the big fake. You can't draw, charges and explain how they function with one force. It's not possible because they have to be, one of them has to keep consuming energy and the other one has to keep radiating it. That still won't work. You can't make the electrons repel and the proton, and the protons repel, and then the electron and the proton attract with one force. Can't be done. There is no Maxwell simulation of electrons and protons. So just understand, and since Maxwell, they've never created a simulation using one force that shows electrons and protons combining. Nothing. Because it won't work. I've tried it. Yeah, okay. which the interactions positive and negative choice were shown to be mediated by one force. Okay, so there's one force in the sense that the force moves the speed of light, but just like there are electrons and protons, there's two kinds of force: proton force and electron force. And that's what you need. You need 2 plus 2 plus 2 physics. You need two kinds of force, two kinds of matter, and two kinds of interactions. That works. That can be simulated, mathematically precisely simulated. There are four main effects resulting from these interactions, all of which have been clearly demonstrated by experiments. So there's more of this promise that they've clearly demonstrated something. Absolute crap. They do an experiment with silver atoms and say they're measuring electron spin. Doesn't make any sense at all. Electric charges attract or repel one another with a force inversely proportional to the square of the distance between them. So that's just like gravity and just like light and just like a paint sprayer and just like about 10 million other things. The inverse square law is just a law of symmetry. So a sphere is symmetrical, it radiates perpendicularly, so therefore the spreading of whatever it's doing, reflecting, it has to spread in two directions. It doesn't have a choice. That's the square. Spreading this way and spreading this way, that's the square. All right. So that's uninteresting. Okay. The inverse square law tells you nothing about the nature of how electrons are different than protons. It says nothing. Magnetic poles. So let's see what they do to this. All right, so we're talking about the difference. Magnetic poles have to be made out of something that's polarizable. The electrons and protons seem the obvious thing that are polarizable. All right, and the obvious thing that you must be stacking to create a magnet. All right, so the magnetic poles must be the electron and proton. The magnetic monopoles are the same as the electric monopoles, electrons and protons. There is no other thing to make a pole out of. All right, for states of polarization at individual points, whatever that means, attract or repel one another in the manner similar to the positive and negative charges and always exit as pairs, even north poles as yoked to the south pole. So whatever that means, right? They just said shit that doesn't mean anything. Magnetic poles, and then they're going to say that they attract and repel like electrons. Yes, of course. Because what are they made out of? Electrons and protons. The electric current inside a wire creates a corresponding, what is this? Circumferential, whatever, magnetic field inside the wire. So again, it's not creating any field inside the wire. It's creating an appearance of the wire. The wire is changing its appearance. All right, it is not inside the wire. Its direction, clockwise or counterclockwise, depends on the direction of the current in the wire. And you have the current moving in the opposite direction of the voltage, which is really idiotic. So again, why didn't you fix that? All right. A current is induced in a loop of wire when it is moved toward or away from a magnetic field. So as it changes what it sees. So if I make a polarized object, you can understand that if you're looking at it from over here, you can see there's two fingers. If you're looking at it directly, you can't see it. And then if you're looking at it from over here, you can see, oh, it's two fingers. So obviously as you move, you change what you see. What something else looks like changes as you change your position that you're looking at it with. That's the obvious truth. The dipoles are can be seen one way and they can't be seen the other way. All right. And obviously as you change your position, you change what you see. Okay. The direction of the current depends on that of the movement. Okay, so it's not saying much. But that's basically the going in is one force, going out, pulling out is exactly the opposite effect. All right, take a pause here. Yeah, I'm back. So I was just pre-reading a little bit of this, and it really is kind of funny later in the paragraph how it's just an illustration of exactly what Wikipedia is doing, exactly what science is doing, is ignoring all kinds of what other people are doing. There's no science here. It's not really about consolidating all the possible references and sources of information and then gleaning the truth. It's just about you're part of our club or you're not part of our club. And that's all it is. It's all this groupthink horse shit. All right, in April 1820, Hans Christian Ørsted observed that an electrical current in a wire caused a nearby compass needle to move. At the time of the discovery, Ørsted did not suggest any satisfactory explanation for the phenomena, nor did he try to represent the phenomena in a mathematical framework. However, 3 months later, he began more intrusive investigations. Soon thereafter, he published his findings, proving that an electric current produces a magnetic field as it flows through a wire. The something unit of magnetic induction is named in honor of his contributions to the field of magnetism. The CGS. Well, that's some sort of honor. Anyway, yeah, it's not exactly called the Ørsted. Anyway, so obviously the point is the wire is incidentally being changed by the electricity. The electricity is doing its thing, and it's creating an effect in that it's changing how the thing looks. It's not radiating any different energy. It's just changing what color photons, so to speak, are reflecting off of the object. So I don't know exactly how to create an analogy to that. But it's got to be understood that a magnetic field is not a generated field. It's not something the thing has to produce. It's only producing it by changing color. It's not doing any work to create the magnetism. That's probably the easiest way to say it. All right, his findings resulted in intensive research throughout the scientific community in electrodynamics. So they paid attention when Ørsted did it, and apparently somebody else did it 100 years earlier, and nobody paid attention. So it's another Mendel story. All right, they influenced French physicist André-Marie Ampère's developments of a single mathematical form to represent the magnetic forces between carriers. So all this love affair with mathematics, Ørsted discovery also represented a major step forward in unifying concept of energy. And obviously they did zillions of experiments. So let's understand, they spun things, they did static electricity, they did all kinds of different experiments. So this wasn't just about theory, it was about investigation. And where's that now? Oh, that's right, they don't do any investigating. All right, this unification, which was observed by Michael Faraday, extended by James Clerk Maxwell, and particularly reformulated by Oliver Heaviside and Heinrich Hertz, is one of the key accomplishments in the 19th century. So, I mean, all this hype, when clearly it's not that profound an observation. I mean, it's almost like you say, yes, of course somebody did it earlier, because you'd almost fall on it by accident. And that's how it was always discovered. I mean, Ørsted did it by accident. Again, it was an accident that he discovered this effect. It wasn't that he was looking for it. It was an accident. It has had far-reaching consequences, one of which was the understanding of the nature of light. So now they're going to talk about their fake nonsense theory that somehow light is a fluctuation in some sort of gooey field or something. Like somehow there's a field going this way and a field going, it's oscillating or something sideways as it moves forward, and just absolute nonsense. Unlike what was proposed by the electromagnetic theory of the time, light and other electromagnetic waves, so they force us to, they keep using this word, it's a wave, when it's not a wave, it's a bunch of bullets, are at present seen as taking the form of quantized self-propagating. So again, what is this self-propagating idea? Is a bullet self-propagating? No, it had to be pushed. Something pushed it. Okay, so yeah, and once it's moving, then you can take its energy, but unless you have some way to take it, it'll go forever. So if you don't bang into it with any other molecules or any other atoms, it'll just keep going. It doesn't need to be self-propagating. Oscillatory. So again, they're assuming that the thing itself is oscillating when no, the pattern is oscillating. There's a bullet, and then another bullet, and then another bullet, and they have a difference in time between them when their arrival times are different. That's the frequency. There's no object vibrating. All right, just so wrong. All right, electromagnetic theory of time, light, and other electromagnetic waves are at present seen as taking the form of quantized, self-propagating, oscillatory electromagnetic field disturbances. So again, it's not a field disturbance, it is the field. The field has the pattern in it, okay? The light rays are made out of bullets. All right, different frequencies of oscillation give rise to different forms of electromagnetic radiation. So the forms are all the same, and all you're doing is changing the frequency. And as you change this frequency, you're also changing polarization, but that's a separate subject. From waves at the lowest frequencies to visible light at intermediate frequencies to gamma rays at high frequencies. And we're talking about really high differences. Okay. Oersted was not the only person to examine the relationship between electricity and magnetism. In 1802, so 20 years earlier, some guy, Juan Domenico Rogojinski, Romagoscani, anyway, Italian legal scholar, so that's kind of funny, deflected a magnetic needle using a voltaic pile. So he put a needle, a magnetized needle, near a battery. The factual setup of the experiment is not completely clear, nor is if current flowed across the needle or not. Well, I don't know how he would measure current across the needle back then. But anyway, the account of the discovery was published in 1802 in an Italian newspaper, but was largely overlooked by contemporary scientific community. So obviously, the fact that they have this, we're special people, you have to belong to our club, then you can submit papers, this whole bullshit. And now, we have the internet, we have all these ways of compiling information and sourcing information. We don't need to have a special publication somewhere. Almost anybody can make the argument. And the science should be rigorous in attempting to find all these arguments or all these experiments and compiling it and finding out what's right about them, what's wrong about them, and all that stuff, and it does none of that. So we haven't advanced at all. What we have is Wikipedia editors saying I have to be banned for life because I disagree with what they're saying I have to believe. So they have to ban me for life for disagreeing. I'm not allowed to disagree. I didn't try to edit anything. I didn't try to do anything. I just tried to have an argument, and they refused to have the argument because Ramanujan seemingly did not belong to this community. So that's the game. Fuck progress, fuck science. It's about our community. It's about our club. It's not about the truth. It's about our religion. And that's all it is. Physics is a religion. All right? It has a strict Bible. You must be a believer. Okay? Or you won't be invited to talk about it. And earlier, 1735, so 100 years earlier, an often neglected connection between electricity and magnetism was reported by Dr. Crook's son. The account stated, a tradesman at Wickfield in Yorkshire, having put up a great number of knives and forks in a large box. So we've seen this quote before. Okay, and having placed the box in the corner of a room. So this is the fact that the knives and forks were magnetized by a bolt of lightning. All right. So again, it was known, but it wasn't known by the people that needed to know. All right, suggested in 1910 that this particular event was responsible for lightning to be credited with the power of magnetizing steel, and it was doubtless this which led Franklin in 1751, so 40 years later, to attempt to magnetize a sewing needle by means of a discharge of a Leyden jars. All right. Obviously, Franklin did a ton of experiments. Amazing. Again, another person you have to just marvel at how he had time to think of so many different subjects and innovate in so many different fields. Just amazing. The electromagnetic forces of the second strongest the electromagnetic force is the second strongest of the four known fundamental forces. So this is just such baby talk about comparing the strength of things in completely different realms. I mean, it's just nonsense. It operates with infinite range. So again, it's only as infinite as any other r squared force. So you can sort of imagine that idea of infinity kind of disappears, because if I go far enough away, I will find a place in space that can't possibly be affected because all of the force has diluted and there's no way for the force to hit it. So in some sense, that's just a lie. There's some place at some distance, in infinity, that will be hit by the force, but there's also a place that will never be hit. Just a fact. Roughly speaking, I don't know where we were. Okay. Roughly speaking, the forces involved in interactions between atoms can be explained by, well, I should finish this weak force, right? Okay, it operates with an infinite range. All the forces, friction is not a force. So here they put friction in here. Friction is not a force. It's just idiotic to call it a force. It's you losing your energy by contact. You're hitting something. Right? It's not a force. Are derived, the force plays a role. I mean, every time you exchange energy, force is playing a role, but you don't call it a force because you punch somebody in the face. That's not a force. All right, are derived from these four fundamental forces. They are known as non-fundamental forces. At high energy and weak force, the electromagnetic force unified as a simple interaction called the electro-weak interaction. So none of these things happen. And they didn't even mention the strong force, which is the idiotic fake force, where they imply that somehow it's hard to bring protons close to each other when, it's really easy. You just stick an electron between them. Roughly speaking, all the forces involved in interactions between atoms can be explained by the electromagnetic force acting between the electrically charged atomic nuclei and electrons. So again, the nuclei is just electrons and protons. The nucleus isn't made out of something different. It's made out of exactly the same crap. It's electrons and protons, little pieces of charge, period. And the electrons are just balancing the excessive positives in the inside of the nucleus. The nucleus has 2 protons for every electron, okay? 2 protons, bingo, electron in between. Now you have 2 protons for every electron in the nucleus, and then you put the rest of the electrons on the outside to balance the forces. Not complicated at all. The underlying assumption being that the protons are heavy, they don't move easily, and the electrons are light and are easy to move. Okay, not very complicated. All right, roughly speaking, the forces involved in interaction between atoms are explained by the electromagnetic force acting between electrically charged atoms, nuclei, and electrons. So again, the electrons are the only things really doing any action. The nucleuses are very hard to get to, so they really don't play much of a role. Of the atoms. Electromagnetic forces also explain how these particles carry momentum by their movement. I mean, duh. You don't need that. The electromagnetic force doesn't show you how the momentum is exchanged. So again, it's just more nonsense. This includes the forces we experience in pushing or pulling. So again, the physics should be able to acknowledge that pulling is always going to be a magical thing. You can't have anything but magical pulls. All right, so it has to be push. It's a push universe. So the physics can't even say that. All right, it has to be a push universe. There's no such thing. Pull is magic, which result from the intermolecular forces that act between individual molecules in our bodies and those of the objects. The electromagnetic forces are also involved in all forms of chemical phenomenon. Okay, well, one more paragraph, we'll call it a video. A necessary part of understanding the intra-atomic and intermolecular forces. So again, it's just charge. It's just the attraction between electrons and protons. That's what's holding everything together. And there's the risk that protons get to see protons and then everything flies apart. Okay, is the effective force generated by the momentum of the electrons' movement. Okay, so yes, the electrons have momentum. They push into each other. When they push into each other, they transfer the momentum. Such as the electrons move between interacting atoms, they carry momentum with them. Yes, like a Newton's cradle, they push on each other and exchange who's moving. Who's moving changes. As a collection of electrons becomes more confined, their minimum momentum necessarily increases due to the Pauli exclusion principle. So this is absolute nonsense. There's no such thing. It's absolute baby talk about some crap that somehow electrons can't occupy the same space. Duh! Who the fuck thinks two things could be in the same space? I mean, it's just so fucking stupid. Yeah, alright. The behavior of the matter at the molecular scale. I mean, I just can't believe this is a real thing. The Pauli exclusion principle. It's just so fucking stupid. All right. I mean, I mean, how do you even explain how stupid it is? You know, I mean, yeah, two bowling balls can't sit on the same place on the rack. I mean, I can't put two cups in the same place on the table. I mean, I can't have two eyes in the same eye socket. I mean, duh. Oh, I mean, god damn it. Anyway, the behavior of matter at the molecular scale, including its density, is determined by the balance between the electromagnetic force and generated by the exchange of momentum carried by the electrons themselves. Well, it's really just about the mass of the particles and their velocity. Momentum is all there is. There's nothing else. That's all there is. It's nothing else. It's all there is. There's nothing else. The whole universe runs on the momentum created by forces hitting matter and making the matter move slower. Faster than they were moving, but slower than the force that's pushing them. So anyway, just such a pile of crap. So we'll see what they do to this classical thing. That's probably nonsense too. Yeah, it's all Maxwell, Lorentz, Poincare, same, you know. These are the people that are going to tell us what we must believe. They get to write the Bible, and then everybody gets to pray to it. It's disgusting. So anyway, enough of a video. Till the next time, and such, and so forth, and whatnot. God, I hate this planet.